Hey, how's it going, everybody? In this Python video, we're going to be going over generators and why you'd want to use them and some of the advantages that they have over lists. So in this example, I have this function up here called square numbers, and what it does is it takes in a list of numbers, and then we have this result variable which is set to an empty list, and then we loop through all the numbers from the list that we passed in, and we append the square of that number to the result list, and then after we're done looping through all the numbers, then we return the result. And then you can see here I have this my numbers variable set equal to square numbers. I'm passing in a list of 1, 2, 3, 4, 5, and then I just print out my numbers down here. So if I run this code, then you can see that our list of 1, 2, 3, 4, 5 that was passed in, our result is 1, 4, 9, 16, 25. So currently our square numbers function is returning a list. Now how would we convert this to be a generator? Well, to do this, we won't need this result variable anymore, so we can take that out. We don't need the return statement. And this result.append, we can take this out. And all we have to do is type in this yield keyword and just yield the square number here. So this yield keyword is what makes it a generator. Now, if I save this and run it, you can see now whenever I print my nums, I'm no longer getting the list. If you look at the comment here, this is what the result used to be. I'm no longer getting 1, 4, 9, 16, 25, the squares of 1 through 5. No longer getting that result. I'm getting this generator object here. Now, the reason for this is because generators don't hold the entire result in memory. It yields one result at a time. So really this is waiting for us to ask for the next result. So it hasn't actually computed anything yet. Now if I printed out next my nums, which asks for the next result, then you can see that it's 1 because we passed in our list of 1, 2, 3, 4, 5, and then we're looping through that list. And so 1 is the first value, so it's equal to I here, and we yielded out 1 times 1, and it gave us that result. So now if we copy this line here and print out next my nums a few times here and run that, then you can see that each time that we run next, it goes and gets the next value that's yielded. So now we have 1 squared, 2 squared, which is 4, 3 squared, which is 9, 16, 25, and so on. Now 25 is the last value from our result. So what if I was to run next one more time? Well, if I do that, you can see that I got an error here, and the exception that it threw was stop iteration, and that means that the entire generator has been exhausted, and stop iteration just means that it's out of values. Now instead of getting these values one at a time, we still can use a for loop on these generators, and this is personally how I use generators a lot of the time. So let me comment out this line, and then let me uncomment that one and save it. So now we're saying for num in my nums, which my nums is our generator, print out num. So I'll run that, and you can see that we get all of our values, and we don't get the stop iteration exception because the for loop knows when to stop before that happens. So one immediate advantage over a list is that I think that this is much more readable here. Rather than having the result set to an empty list and then appending to that result and then returning the result, this is kind of more readable. We're saying, okay, I'm passing in these numbers for each number in that list of numbers, yield the result. Now, for those of you more familiar with Python, you might have noticed that this entire process here of these lines of code would have been much easier to write as a list comprehension. So let me comment this out. And if you don't know what a list comprehension is, don't worry about it too much. I just want to show the generator example with this as well. Now this is a list comprehension here, and it's going to do exactly what our square numbers function did. So what we're doing is we're creating a list, and we are taking x times x, so the square of x, for x in this list of 1, 2, 3, 4, 5. So if I save this here and run the code, you can see that I still get the same results, and I can also print out this list up here at the top. Now you can create a generator in the same way And it's just as easy as taking out these brackets and instead putting in parentheses. So if I take out those brackets, put in parentheses, now if I run this, then you can see that when I printed my nums here, I tried to print it all at once, I got that generator object, and then when I ran my for loop, it looped through all the values and gave me that result. Okay, so what if you wanted to actually print out all of the values from the generator? Well, like I said, they're not currently all held in memory, but you can convert it to a list, and it's just as easy as just putting list and then wrapping that. And then if I run that, you can see that it printed it out just as if it was a list. Now, when you convert this generator to a list, then you do lose the advantages that you gained in terms of performance. And I haven't talked about performance yet, but I have a better example to show those advantages. So a generator is better with performance because, like I said, it's not holding all the values in memory, which isn't a big deal at all whenever you have a small list like this of 1, 2, 3, 4, 5. But say that you had tens of thousands or even millions of items to loop through, then having that many items in memory will definitely be noticeable, but you don't get that with generators. So whenever you cast a generator to a list like this, if this generator had a lot of values that it needed to convert to that list, then you lose that performance in terms of it would put all of those values into memory. So let me show you a better example here of this performance difference. So I have a file here where some of this stuff you don't have to worry about. Like these lines here, I'm just printing out the memory, and then these names and majors, these are just going to be used to make some random values. So I have two different functions here. One of these is going to make a list, and one of these is going to be a generator, and they're both returning the same values. So within this list, I have my result here, and I'm looping through a number of people that I'm going to pass to this function. And for each person, I'm just going to make a person dictionary, give it an ID and a name that's randomly chosen from the list of names up at top, and a major that's randomly chosen from the list of majors. And then I'm going to return that result. And for the generator, it's the exact same thing. I'm going to loop through the number of people that I pass in, and then I'm going to yield this person dictionary that has the same values as the list function had. Now really quick, just to make these the same, I'm going to make that an X range instead so that these are exactly the same. Okay, so right here, don't worry about these lines here, this time.clock and this T2 time.clock. All I'm going to do is time how long it takes to run this function which returns a list. Now I'm going to pass in 1 million values to this function, so it should return a list of 1 million results. And then down here at the bottom, I'm printing out the memory usage and the total time that it took. So if I run this, then you can see up here at the top of the code, so this before here, this is before I made anything. So my base memory usage was around 15 megabytes. And this memory after is after I created that list of 1 million records. So you can see here that it jumped up by nearly 300 megabytes, and it took 1.2 seconds. Now, if you're dealing with large amounts of data, that's not out of the ordinary to have 1 million records like that. So let's see what this looks like if I instead use the generator example. So I'm going to comment out the function that returned a list, and now I'm going to uncomment this function that returns a generator, and I'm going to pass in the same number of values. I'm going to pass in 1 million values here. So if I save that and run it, now you can see here after I ran this that the memory is almost exactly the same, and that's because the generator hasn't actually done anything yet. It's not holding those million values in memory. It's waiting for me to grab the next one or to loop through those, and it would give me those one at a time. Now this time that it took here, basically it didn't take any time because as soon as it gets to the first yield statement, it stops. So if I was instead to make this an integer, then it would be nearly 0 seconds. Now, whenever I said earlier that if you convert this to a list, then you lose that performance, then let me show you what I mean here. So I will convert this result, this entire result, to a list. And now, if I run this, then you can see basically I got pretty much the same result that I got when I ran the function that returned the list. So if I take these back off and just do the generator, then you can see that we get our performance back. So that's how you use a generator. I think that it is a little bit more readable, and it also gives you big performance boosts, not only with execution time, but with memory as well. And you can still use all of the comprehensions and this generator expression here, so you don't lose anything in that area. So those are a few reasons why you would use generators, and also some of the advantages that come along with that. So I hope this video was useful for you guys. If you do have any questions about this stuff, just ask in the comment section below. Be sure to subscribe for future Python videos, and thank you guys for watching.